Okay, let's continue. Does everybody hear?
Dmitry Alexandrovich, I didn't quite understand the purpose of the last activation function. Can we talk about it?
Okay.
What
You mean
was
this one?
Yes. It's not differentiable at zero, at the point zero.
You may check directly that it has a continuous derivative at 0 point.
The right derivative is 1, and the left derivative is alpha. Unless alpha is equal to 1, it's not.
Well, no, derivative is alpha times exponential.
Exponential function at point 0 is 1. 1 times alpha is alpha.
Yeah, it's true.
Just a second. So derivative is alpha times exp. At 0 it is alpha. Yes.
Did I understand correctly that the point was to have continuous derivative at point 0?
Yes, the point is to get some activation function that is continuously differentiable everywhere. Just a second, I'll see the.
We can let alpha be equal to 1 or have exponential function of z divided by alpha.
Exponential function, yes.
Of what? How do you propose z divided by alpha?
Yes, under the exponential function z divided by alpha.
Okay. Yes, maybe right. Anyway, the point is to get some something like this everywhere continuously differentiable function which has one slope on the positive side and different slope on the negative side. However, again, in practice, this particular activation function is rarely used, only if for some reason you indeed need everywhere differentiable function. Okay, well, now let's continue our discussion. So let's return again to the optimization problem that we have here for learning logistic regression, or this similar situation, but when your score function is calculated by a multilinear perceptron. So you need to solve this optimization problem, and the straight way to do this is to use some gradient type optimizer. So you implement the calculation of your score function and also the calculation of the gradient of this function with respect to parameters, put it inside some optimizer like stochastic gradient descent or Adam, and get the answer. In principle, it is possible to, well, generally speaking, to use what is called a derivative-free optimization. So when you just implement the forward pass through the network, just the calculation of your loss function, and do not use any derivative with respect to parameters, and do an optimization. This approach is sometimes used, for example, within reinforcement learning, where your rewards is usually assumed to be a non-differentiable function. And in this case, sometimes people use derivative-free optimization and get more or less good results. However, generally speaking about optimization, if we compare gradient-based optimization and derivative-free optimization, usually gradient-based optimization works much more efficient. So it requires less number of iteration. It has better theoretical guarantees, etc., than derivative-free optimization. So if you are able somehow to calculate the gradient of your function with respect to parameter, you better do this. So our topic for discussion for the last part of the lecture for today is, well, actually, how can we find the derivative of this function, where this function may be calculated in some complicated way with respect to all the parameters on computer. So let's first reason about this problem, well, from some general viewpoint. Let's take an example. Suppose that we have a three-dimensional function, the following three-dimensional function. And our problem, our question is the following. So given this function and the input x1, x2, x3, we would like to find the gradient of this function with respect to all the variables. So the vector of partial derivative like this on computer. So that is the problem. What are possible ways to solve this problem? Generally speaking, we may reason about at least three possible different approaches. The first approach comes from mathematical analysis, the first course. Do a symbolic derivation. So you have some particular expression for a function. You take pen and paper, write down using derivative calculus the necessary formula for calculating the analytical expression for the derivative for all these three partial derivatives, and then, well, implement these formulas as a computer program and get the result. Such approach is not, well, very efficient in general case, because if you do calculation this way, you always get some, well, quite long or even huge symbolic expression, and calculating this expression in computer program would be quite difficult to do, and also to derive this analytic expression on paper, not in this simple case, but in case when you have a neural network with a lot of layers, and in each layer you have matrices of parameters, or in more general situation, even tensors of parameters, it is not possible to do. Yes, some question? No? Okay. So the analytic derivation is not an efficient way to do something in computer when you calculate the derivative. The second option, which can be done, is to use finite differences. So we may say that, suppose that you have implemented somehow the function itself that you need to calculate, and then you may say that the derivative with respect to some variable can be approximated in the following way. For some small enough epsilon. So here this EI is just a vector with all zero component except for one on i's position. Epsilon is some small number, some small real number, and if you have a procedure for calculating the function itself, you may calculate the partial derivative approximately using infinite difference. What are the problems with this approach? Well, actually, the first problem here is that this calculation is not very accurate. because we do all the calculation on computers in float numbers. From theoretical point of view, this formula comes from Taylor expansion of a function in the vicinity of the current point x. And theoretically, if we take this epsilon that is close to 0, the closer it would be to 0, the more accurate would be this formula approximating the true partial derivative. However, if we calculate this formula using float numbers, for quite small epsilon here, we have a difference of two values which would be very close to each other. And you know that all calculation on computer goes with respect to machine precision. And if you do operations like addition of some big number with some small number, you may lose the precision in the result. And in a similar way, if you do a subtraction of two very similar values, again, the result may be not very accurate because of the floating point arithmetic. And that is the case with this formula. So it can be proven that if epsilon m is machine precision, then the best you can do from this formula, you may take as this epsilon the square root of machine precision, and the difference between these two things, the accuracy of this formula, again, would be at best it's just the square root of machine precision. So if we do all the calculation in doubles in 64 bits, our machine precision is approximately 10 to the power of minus 16. So the square root of this value is only 10 to the power of minus 8. And if we do calculation in floats, I mean in 32 bits, which is, by the way, the general situation when you do some calculation on GPU. On GPU, people usually use 32 bits arithmetic. So for float, your machine precision is about 10 to the power of minus 7. So the square root, this accuracy would be 10 to the power minus 3 or only. So this formula would be, well, not accurate at all. And the situation is even worse if you use not 32 but less number of bits in order to accelerate your neural network. So the first and quite big problem with this formula is that it is not accurate. However, it is possible to calculate a finite difference, well, in a more accurate way. And I'll show you how we can do this. So again, all finite difference derivation are derived from Taylor expansion, this or that Taylor expansion of our function in vicinity of the current point x. So we have our function f of x, and consider this function in the following point. So here x is some vector, p is some vector, epsilon is a small number, and here this I is a complex unity. So what we do here, initially we have our function as a real valued function. And we do what is called a complex expansion of this function into complex space. So we consider some function that depends now on complex number, so it's complex valued, in such a way that along the real line, this function coincides with our initial real valued function. Fortunately, this components expansion may be done uniquely for the function that is infinite time continuously differentiable. If your real valued function is infinite time continuously differentiable, you may expanded to the complex space in a unique way. And moreover, if you use like NumPy or PyTorch library for organizing all the calculation, you don't need to think about how to do this complex expansion at all, because you have some implementation of your function in standard functions like exponents, summation, subtraction, sine, cosine, etc. And if you take as an input to your function some complex number, NumPy or PyTorch automatically interpret all the function at their complex versions, and calculate everything in complex number. So you just take this complex point and work with a complex expansion of this function. So now we do a Taylor expansion of it around the point x. What we get, it is f of x plus the gradient f of x times this point, the difference between x plus I epsilon p and x. So this I epsilon p. That is the first term. Then the next term would be something that corresponds to second derivative. So formally it is 1/2 our point transpose times Hessian times our point. So you see, this we have I squared. So I squared is just -1. So we may say that this function in terms of epsilon is just big O of epsilon squared. So it's some real valued term with this dependence on epsilon. And the last term, the second, which somehow corresponds to the third derivative, we have I epsilon p times I epsilon p times I epsilon p. So I at the I cubed, this is minus I, times the third derivative. So we may say that as a function of epsilon, this would be some imaginary part plus I times big O of epsilon cubed. So that's all. That is our Taylor expansion. And what we need here, we need to extract this term, the gradient times p, in order to calculate it using finite difference. So let's do this. So first of all, let's take imaginary part from this Taylor expansion. What we would get? This is the real thing, this is the real thing, and these two are imaginary thing. So we may write down that this is just times epsilon plus epsilon cubed term. And then in order to extract this thing, we may write down like imaginary part here. And then take this epsilon to be some small value. So we do not have this term if epsilon is small enough, and our approximation to this expression, to this gradient, can be calculated in this way. And now if we need to find out the partial derivative with respect to a particular x, so the partial derivative with respect to xi, this is exactly the same as to calculate this inner product where p is just a vector ei, i's ort. So what can we say about this way of calculating derivatives? You may note that here we do not have a subtraction operation. We do not, in the denominator, we do not have a subtraction of two very similar terms. And because of this, we can calculate this expression very accurate, almost to up to machine precision. So comparing to the first method, where our best accuracy was just the square root of machine precision. For that particular scheme, for calculating this expression, we have the accuracy that is just machine precision. And our epsilon, we may take epsilon of arbitrary low value about approximate to machine precision. So if we calculate everything in doubles, we do almost exact calculation of our gradient using this type of scheme. So this problem of accuracy is completely solved with this method. However, let's think about the number of calculations that we need in order to find all the components of our gradient. You see that in order to calculate this thing with respect to all xi, we need to do this or some other finite difference calculation for all possible for all dimensions. So for A1, for E1, E2, E3, etc. For each feature, in order to calculate our gradient vector, we need to do the calculations that is proportional to the dimension of our vector x. And if we speak about neural networks, when it could be easily like a million of parameters to find, it means that calculation of gradient using this method would cost us 1,000,000 times more comparing to the calculation of function f itself, of making a forward propagation through our neural network. So it would be too long, prohibitively low for calculating gradient in this way. However, this is, well, very simple way to calculate the gradient if you have an access to the function itself. So this procedure is a good way to check yourself. For example, you somehow implement your function and implement the calculation of derivative of your function, and you would like to check yourself whether you do everything correctly. You may use this type of calculation and understand that everything is done correctly. So that was the second approach. And yes,
I have some questions. The first one I didn't get. Why the accuracy for the first method? No, for finite. Yes. Why here accuracy is square root of epsilon?
Well, it is possible to derive this thing because if you consider different epsilons here, so the true expression will be like this. So here you have a linear dependence on epsilon. So if you try to decrease the epsilon, you decrease this term, but till some point. After some point, you will have the situation that these two values would be very close to each other, and decreasing epsilon would increase the error in the first term. And when you try to explicitly derive what is the optimal epsilon would be in this calculation, you need to take a situation when the accuracy here and accuracy here would be the same. And this corresponds to the square root of machine precision.
Yes, okay, thank you. And also you said in the end of this method that it can be used to check another ways to calculate gradients. And so are there some libraries that provide this functionality to check derivatives?
You don't need to have a library here. Look, what you do here is just one formula. So you have already implemented your function f. So the only thing you need to do is just to call this function at this particular point. So it is one line of code. You don't need.
Yes, but you have to remember this expression. Okay. So yeah, understood. Thank you.
The only restriction, just one note, the only restriction for using this method is that your function f should be infinite time continuously differentiable in order to make a correct expansion to the complex space. By the way, if you formally apply that method to your neural network with a ReLU activation function, ReLU is not everywhere differentiable. The operation max do not have a unique correspondence to the complex space because it is not evident what does it mean max between two complex numbers. However, if you implement the ReLU function not with a max operation, but as an if operator, like if argument is greater than 0, then return this argument, or otherwise return 0. If you do this in this way, then this method with a complex point would work well. So you say that if you are standing somewhere here, you approximate your activation function with just this line, and if you stay somewhere here, you just approximate your activation function with this line, and that would be a completely infinite time continuous differentiable function, and that works also here. Okay, now let's do the third approach, which is actually used in practice for calculating derivatives for neural networks, which is called the automatic differentiation. So calculating the derivative using the computational graph of the function. So what we do, again, here is this example with our simple function depending on 3 variables. So the first thing we do is we transform this function into computational graph. In computational graph, we have as an input our 3 variables, and then we just say what should be done in our code in order to implement this function. So we may say that, well, first we need to calculate the product of x1 and x2. Let's denote it by x4. Also, we need to calculate the sign of x3. Put it here. Then calculate an exponent. Calculate sign on this as a product. Then take a sum of these two, x8, and finally x9, which is a division of x8 times x3, and finally the output is our function f. So this is the computational graph for this particular function. In this computational graph, each node corresponds to a particular variable, and the edge, each arrow corresponds to a particular arithmetic operation that is used with the input variables here. So generally speaking, if we have some analytic expression, the computational graph for this expression can be constructed in non-unique ways, and well, there exist some techniques on how to construct this computational graph in the most efficient manner. However, if we speak about our practice about calculating derivatives on computer, actually you construct this computational graph by implementing this function. So when you implement it on computer, you just write down your code. So first calculate the product, then a sign, then take an x, and so on. And making your code is equivalent to introducing some particular computational graph for a function. Okay, and when you have this thing, you may now apply what is called automatic differential technique for calculating derivative. And this automatic differential techniques, generally speaking, has three possible modes for calculating the derivative. First is forward mode, the second is backward mode, and the third is what is called cross mode. Let's quickly consider all three cases. So the first option is to do a forward mode. In forward mode, as it goes from its name, we just go through our computational graph from left to right. So what we need, finally, we need to calculate the partial derivative of our function with respect to three inputs, x1, x2, x3. So let's consider calculation of, for example, with respect to x1 when we go in our computational graph from left to right. So first, we initialize our derivative by considering the derivative of the input variables with respect to a fixed x1, for example. So this is equal to 1, derivative here equals 0, equals 0. So we initialize our procedure on the input of our computational graph. Then move to the right and first calculate x4. This is needed in order to calculate finally our function f. And so we calculate x4 as a product of these two. And simultaneously, we calculate the derivative of x4 with respect to, say, x1. So calculate it using simple derivation rules like a derivative of a product. So it would be like this. And we use these two derivatives from the previous iteration from our initialization. In similar way, if we need to calculate, say, x5, which is the sine of x3, then we calculate this derivative using chain rule, cosine of x3 times derivative of x3 x1. So do the first step of calculating, if we know the values, all x's, and the derivatives of these x's with respect to some fixed variable, we may recalculate new values x here and the derivatives of these x's with respect to our fixed variable. Then we do it to the next layer, and so on. And finally, calculate the derivative of f with respect to x1, and this would be the answer. What about the computational complexity of this way of calculating the derivative? So look, suppose that let's write down here. So the value and computational cost. So suppose that calculation of our function at some point x costs us big O of q. So this q is just one forward propagation through this graph. Then what about the calculating of this partial derivative by forward mode? Comparing with this big O of q, how do you think? What would be the cost?
It will be the same big O of q.
The same, yes, because for calculating this derivative, we need to make a forward propagation through the same graph, so to go through the same variables, and on each edge we do a calculation that are similar to the calculation of the variables x themselves. Because look, for example, here, for calculating x4, we need to take a product of something. To calculate the derivative, we again need to calculate the product and one sum. Here, we calculate a sine. For calculating derivative, we calculate a cosine, which is the same in time calculation. So calculating a particular partial derivative by forward mode costs us the same thing as the calculating of the function itself. However, what about the full gradient? The vector of all partial derivatives of f of x. What would be the cost of this procedure? Again, by forward mode.
O of q times the number of arguments of f.
Yes. Time dimension, in this particular case, times 3, because we need to do a forward mode the number of times proportional to the number of variables we have, calculating derivatives vector x1, x2, x3, etc. So for the forward mode, we have exactly the same product, the same problem as we have in this finite difference calculation. We need to calculate it for each possible variable, and for narrow network, this d would be a huge number, maybe a huge number, and this forward mode would be absolutely inefficient for calculating gradient in this case. So that is why people usually use what is called the backward mode for calculating derivative, which is, well, actually the same thing, but we go in our computational graph from right to left. So initially, we calculate, well, let's do like this, the partial derivative of the output with respect to the output. On the next step, we calculate the partial derivative of the output with respect to current intermediate variable that we consider. So in this case, with respect to x9, and since f is equal to x9, this is also 1. And the next step, df with respect to x8. This can be calculated using a chain rule. So the derivative of f with respect to x8 is a product of derivative of f with respect to x9 times the derivative of x9 with respect to x8. So we just write down this way. This derivative comes from the previous step, and this derivative can be calculated directly because x9 and x8 are connected with h, with h. So here states some particular analytical function, and we may calculate the derivative of it exactly. So here we write like times 1 over x3. And go in a similar way to the left in this computational graph. For example, if we need to calculate the f with respect to x4, what we do? The derivative of f with respect to x4 depends only on derivatives that are stated here. So it would be a sum. The f with respect to the x6 times plus x7 x4. So these two things comes from the previous iteration of our algorithm. These two derivatives are calculated directly from our expression, and in this way we calculate all the derivatives. And finally, on the last step, we calculate all three derivatives. So on the last step here, when we go from right to left, we go through three derivatives df with respect to all the input variables. Okay, now let's continue this table. What can be said about the costs of calculating the gradient of f by backward mode?
It's O of Q.
Yes. So it does not explicitly depends on the dimension of our input space, because for the backward mode, we go through our computational graph only once from right to left, and on the last step, we already have not just one partial derivative, but all the required partial derivatives. So we do only one propagation through our graph and get the answer. It means that for the backward mode, for this particular real valued function, the calculation of gradient costs us the same value up to some constant to the calculation of our function itself. The price for this efficiency comparing to the forward mode is memory, because in order to do the backward calculation, we first need to do the forward calculation for the function itself, and then store into memory all the intermediate access here, because here, for example, when we do some calculation, we use our intermediate variables to do the calculation. So we need to store all this thing into memory, and if your computational graph is huge enough with quite huge intermediate terms, these memory requirements can be quite huge. So that is the price for efficiency in calculating the gradient in the backward mode. However, if we speak about neural networks, in neural networks, our common situation is the following: that number of input variables can be very big. This is number of weights in the network, but the output from our network is always one-dimensional, because this is the value of our loss function that we minimize. And because of this, in neural networks, the gradients usually calculated by using the backward mode. And finally, just for you to know, also quickly consider the cross mode.
Dmitry Alexandrovich.
Yes.
In the forward mode, should we also store all the gradients, all the partial derivatives?
No, because in forward mode, suppose that you calculated x4 and x5 and the derivative of x4 and x5 with respect to the required variables. Then, when you go to the next layer, you don't need to store, for example, the initial variables x1, x2, x3. For do calculation on this layer, you need only information from the previous layer. So when you do the calculation, you may clear the memory from the previous layer and do not store anything in memory except for the current layer when you do calculation. So forward mode do not require you any memory.
Okay, thank you.
And now about the cross mode. For cross mode, let's consider the following situation. Suppose we have a vector valued function. So we have several inputs, x1, x2, xd, and several outputs, f1, f2, m. So many inputs, many outputs. And for example, we have a calculation graph of this type. I don't know, somehow we using these input variables, we'll calculate the intermediate factor y, and y is supposed to be one-dimensional. And then from y, somehow we calculate the vector output. And so suppose we have such type of computational graph, and try to find the best possible way to calculate the Jacobian in this case, so the partial derivatives of all the outputs from the network with respect to all the inputs to this computational graph. So what would be the best possible way to organize such calculation, forward mode or backward mode?
I think the best will be to have the forward mode in the part from y to functions f1 to fm, and backward in the part from axis to y. But
or y to axis. Yes. So if you apply the backward mode, for example, for the whole computation graph, you need to do the number of propagations that is proportional to the number of outputs. So doing the backward mode, you calculate the derivative of some current output fi with respect to some intermediate variable xj. So the number of backward propagation would be m. If you calculate the derivative in forward mode, the number of forward propagation would be proportional to d. However, if you calculate first the derivative of y with respect to all the variables xi, all the input variables, you need just one backward propagation here. And in order to calculate the derivative of all fj with respect to y, since y is one-dimensional, you need just one forward propagation here. So here we do a backward propagation, and here we calculate the derivatives in a forward way. And then we just combine. So our derivative with respect to xi is just a product. In this way. So this would be the best possible way to calculate the derivative. And this is what is called a cross mode. And there are some libraries that, well, try somehow to analyze the computational graph you need for a particular function and try to find these thin places and optimize the way to how to organize the derivative calculation. However, this cross mode is, well, not quite often used in practice because, again, particularly for neural networks, we always have a one-dimensional real valued function, which is just our loss function. So the output is always one-dimensional, and we usually calculate the derivative using the backward mode, and that's all. So returning to our multi-layer perceptron. In multi-layer perceptron, we have a computational graph of the following type. So now we may interpret all the intermediate terms as vectors. So here input x, some weights of the first layer, calculate z, then activation, etc., etc. And finally, we have the loss function L. So in order to calculate the gradient of L with respect to all W's, the only thing we need to do is to understand how to do a propagation of the gradient with respect to each edge in this graph. So having, for example, if we consider just one step, one layer, so we have some input x, we have some parameters w, calculate z, and calculate a, and then go to some function L. So we need to understand just two things. that given the gradient of L with respect to activation A, find the gradient of L with respect to Z. And then, given the gradient of L with respect to Z, here find the gradient of L with respect to W and the gradient of L with respect to X. So this gradient with respect to W, it would be the part of our desired gradient, and the gradient with respect to X would be used for calculation on the next level. And so we calculate our derivative in the backward mode with respect to all the parameters in the network. That is what we need to do. However, the important thing is that we need to do all these computations to take derivatives with respect to matrices and vectors, because these are not just numbers. So we may not use our calculations here from this simple example where here always stays a one-dimensional derivative. So we calculate the derivative in a simple way. Here, for example, in this computational graph, we need to deal with matrices and vectors. And well, in a more general case, for example, for convolutional neural networks, we need to do a calculation for four-dimensional tensor or sometimes for many-dimensional tensor. So before we may explicitly derive this formula for calculating the gradients, we need quickly discuss how to calculate derivatives for matrix mode, for matrix expression. So that would be our next part for discussion. So what is the problem? Consider that we have some matrix valued function. Well, not matrix valued, but like this. Here, X is some vector, A is some matrix n times n, and F is a real value function. And we need to calculate the gradient with respect to X, like this. I mean, calculate it analytically by pen and paper. What would you do? So one option is to write down this expression with respect to each component of X. So write down here is a two-dimensional sum all xi, xj, and then calculate the partial derivative of f with respect to a particular xi using its components-wise expression, and then return back to the vector expression for the gradient of f. Well, this approach does not work in almost all the situations when we have some matrix expression, because, well, for this simple case, it is indeed possible to come to individual components and calculate individual partial derivatives. But if you somehow increase the complexity of your matrix equation, you quickly lose the ability to express what you need to calculate in terms of individual components. So for example, suppose you have now a matrix valued function f of x. Just a second. Camera need time to focus. Okay. So now here x is some matrix, n by n, a and b are some parameters against some matrices, and we have, for example, this expression, some matrix valued function f of x. And again, you would like to calculate the gradient of f with respect to x. In this time, this would be the matrix of partial derivatives of f with respect to each component xij. And if you look to this expression, it would be very hard for you to re-express this in terms of individual xij, especially for this inverse matrix, for example, because the expression for inverse matrix requires u Jacobians of some submatrices. So it is always almost impossible to express it using individual variables xij. And what we need to do is to understand how can we calculate this gradient directly in terms of matrices or in terms of vectors. So for this particular example, what we would like to have, we say that, well, okay, we would like to calculate the gradient of f with respect to x, where now x is already a matrix. So the gradient with respect to x of this trace, and the trace of a matrix is a linear operator, so it would be natural, if you have some linear operator, to exchange the derivation operator and this trace, and to write down something like this expression, and then use the derivative of a product, so something like a and b are just some constants that does not depend on x. So it would be a times dx, regardless what does it mean, plus ax, b. So something like this. So we would like to calculate the derivative of our function in, using matrices, using, this type of operation. However, this would not be, look at this expression, the dx by dx. So what does it mean? Actually, it means a four-dimensional tensor, because here you may consider the partial derivative of every component of matrix X with respect to every component of matrix X. So this is a four-dimensional tensor. The same is here, because we calculate the derivative of a matrix with respect to a matrix. Again, a four-dimensional tensor. Then we multiply four-dimensional tensor by two-dimensional and then take a trace. Well, in principle, it is possible to calculate this expression this way. However, you see that this leads to changing in dimension of intermediate calculations. And if you use some tensor calculus, which allows you to change the dimension of your tensors, in principle, it is possible to calculate the derivative in this way. However, in practice, the tensor calculations have some heavy notation. It is even there exist even several possible ways to introduce notation for tensor calculation, and it is not very easy to do everything with this expanded tensor notation. So for us, it would be much more easier to calculate the derivative that saves the dimensionality of all the terms. So if initially our function f requires only matrices in order to calculate the function f itself, we would like to have a way to calculate the gradient of this function also operating only with matrices, without all these tensors that are stated here. And well, in practice, it is possible to do this. The only thing is that we need to change the object that we calculate not increasing the dimension of intermediate calculations. So instead of this partial derivative of our function with respect to each input, we need to consider what is called a differential of a function. And in terms of a differential, the dimension would be preserved. So in informal way, suppose that we consider any transformation, any function from some space U to space V. And this U and V, we require that that should be linear normed spaces. So they are linear, meaning that they are closed on a linear operation. So two elements, the sum of two elements from this space is again an element from this space. And norm, meaning that it is possible to introduce a norm notion with the corresponding axioms. And then let's consider this thing. So we consider our function f at point x plus some increment h. And if our function is differentiable, it means that this thing always can be represented in this way. So the difference between these two things can be expressed as some linear operator with respect to the input h. So if x is fixed here, this function as a function of the increment h is a linear operator. So if we fix this x, so this differential take an element h, which is an element from U, and outputs what? The element from V, from the same space as where the f lives. So like this. And this is what is called a differential. Plus some small term depending on h. So as you may note, the dimensionality of the function f and the differential here is absolutely the same. These are both functions from U to V. And calculating the differential, it is possible by not increasing the dimension of intermediate calculations. So next, we need to understand on how to, well, for real function, how to calculate these differentials. This can be done in the same way as you calculate the partial derivative of a function, because for partial derivative or for just simple one-dimensional derivative, you have a definition of what does it mean. This derivative as a limit of some expression. However, in practice, you do not calculate the derivative of a function using the definition. And instead, you use, well, two things. First, you use the table of standard derivatives for one-dimensional case. You know that if you, I don't know, have some simple function like x to the power of n, its derivative looks like this. Or if you have an exp, its derivative is an exp itself, etc., etc. So you first know the table of derivatives of standard functions. That is one thing. And the other thing, you use the rules for calculating the derivative for standard operations like summation, product, division, etc. You know that the derivative of a sum of two functions is just a sum of two derivatives. So the derivative of a product, etc. Standard rules of derivations. So absolutely the same thing is true for this differential. We may introduce first the table of standard differentials for some simple functions, and also the table of rules how to calculate the differentials for differential of a sum, differential of a product, and so on. So let's just write down these two tables for the case of differentials. So standard functions, differentials of standard functions. So first, let's consider the linear function. So x is some variable with respect to which we calculate the differential. C is some fixed vector. So the derivative of this function would be that thing. Then the derivative of a quadratic function can be written in this way, or if our matrix A is actually symmetric, it would be just like this. Then consider trace of a matrix. Trace is a linear operator, so for all linear operator, we may use this expression. Then the determinant of matrix X, which is just a determinant times trace, and the inverse matrix, which is just this expression. So these are some standard differentials of table functions, let's say. And then also we need a table of rules on how to calculate the derivative, the differential, sorry. Well, these rules are quite standard. The differential of a sum is just a sum of differentials. Differential of a product can be calculated in this way. Differential of a ratio and in this case we suppose that phi is actually one-dimensional function. So what else? And the last rule is a chain rule. So if we have a superposition of two functions, how to calculate the differential of this function? So if we have f of x, which is f of g of x, and this g of x is y, then differential of our function f can be written down this way. So this is the differential of f as a function of variable y. So depending on y with increment dy, and at the same time, instead of the differential dy, we may put the differential of g as a function of x. So like this. So that's all. That's all the standard rules. And now, well, just for simplicity, let's consider some example. By the way, let's start with this, the last standard function, standard differential. Let's try to derive it, how to calculate the differential of the inverse matrix. Calculate the derivative of the inverse matrix. So what is the inverse matrix? By definition, inverse matrix is some matrix that the product with X is equal to unity matrix. Then take a differential of both types, of both parts here. The left part is differential of a product using this rule. We may write down that this is differential of inverse matrix times x plus inverse matrix times dx is equal to differential of a unity matrix, but unity matrix is a constant matrix. It doesn't depend on any variable, so this is just a zero matrix. And finally, we need to extract this thing. So we put this expression to the right, then multiply both sides by inverse x, and finally get the answer. And this thing is okay. One more example. Suppose that we have something like this expression. So it's a real values function that depends on x, where x is some matrix and a and b is also some matrix. And we suppose that these matrices are not square. So we are not able to split the determinant of a product as a product of determinants here. So, and again, we need to calculate the derivative. The differential of f with respect to the matrix x. So how would we do this? So differential of that. Just use our rules for differential of a determinant is written here. So it is a determinant times trace of xb inversed time differential of the argument. But now the argument is this product of ax b, and finally the derivative, the differential of a product here again using these rules and considering that a and b are just constants, so the derivative, the differentials of a and b are zeros, we get that this is a times dx times b. And finally, for simplicity, under the trace, if we have a trace of a product of something, we are allowed to do a cyclic shift. It would be the same thing. So we may write down that this is equivalent to trace and move b to the first position times a times dx. So just in a couple of lines, we calculate the differential of quite a complex expression involving determinants, determinant, and some matrices. So you see, very easy. However, to the current point, we still not able to calculate the partial derivative of f with respect to x. Okay, let's say that we have calculated something that is called a differential, some linear operator, but it is not clear what is the connection between this differential, this linear operator, and the common notion of derivative, the partial derivative, etc. And in order to connect these two things, people usually use what is called a canonical form of differential. So this is a table that connects differential and the gradient, the partial derivatives. So we write down this table as a 3 by 3 cases. So this U and V are our possible input and output space. And for simplicity, we consider 3 situations when each of these space could be either a real value, a vector, or a matrix. So this U could be real value, could be some vector, or could be some matrix n by m. And the same with V, real value, some vector of different size, or some matrix. And here we put the expression for differential in each of these 9 cases. So the first case is very simple. We have the common one-dimensional real valued function, and in this case, our differential can be expressed just like this. So this is just a product of usual derivatives times increment times dx. Next, if you have vector valued input and scalar output, then again our differential, which is a linear operator, can be expressed as an inner product of the gradient, which is now a vector, times dx, the increment, which is again a vector. So this is the inner product of two vectors, which combines to the number equal to a differential. And for matrices, again, we need to calculate the inner product between the matrix of partial derivatives times the increment dx. So this is this, well, the inner product of these two things. Now, these are two matrices. This is a matrix consisting of all partial derivatives, and this is again the matrix that is an increment, and the inner product in the space of matrices can always be written as a trace of the first matrix transpose times the second matrix. So this is the first column. Now the first row, input is always one-dimensional, output may be multi-dimensional. So here we have this thing. Now this dx is one-dimensional, and this f of x is a vector of partial derivatives of all the partial derivatives of the output of fi with respect to the input x. And here, the similar expression. Again, this is number and this is matrix. A matrix of the partial derivatives of all the outputs with respect to the input x. And one more case when we have vector input and vector output. In this case, this would be the product here dx is a vector, and here states a Jacobian. Jacobian is a matrix of partial derivatives of all the outputs with respect to all the inputs. So this is Jacobian matrix. And 3 remaining cases. Here we cannot write the expression in terms of only matrices and vectors, because here, for example, we need to represent a differential using partial derivatives, which would be 3-dimensional, because we need to consider partial derivatives of all the matrix here with respect to all the inputs. This is a 3-dimensional tensor. So here, in these 3 cases, we need to put expression in tensor calculus. So we would not do this because, for simplicity, we try to work only with vector and matrices. And so this is the standard table. Now let's return to our example, this one. So we have already calculated the differential of our f of x. And now the question, what would be the gradient of this function with respect to x, this matrix of partial derivatives? How can we answer this question? Very simple. The only thing we need to do is to convert the expression for our differential into canonical form, to the form like this, and from this canonical form extract the expression for derivative. So this is the case when we have matrix input and real output. So this is the case in the table that stays here. So we need to transform our expression for differential in terms of trace of something times dx. And this, if we succeed with this, the expression that is stated here would be exactly the desired gradient. So now let's look here. This determinant is some number, so we may put this number inside the trace, and in this way we have the required equation: trace of something times dx, and this something transposed would be our answer. So the gradient of f of x is just determinant times a transposed axb minus transposed b transposed, because the taking transposition of a product, we take individual transposition in an inverse order. So in this way, and minus transpose means it is always the same. Take first the inverse and then transpose, or first take transpose and then inverse. So we may write down this in one term minus t. So that is the gradient of f in terms of metrics. Okay, now having this knowledge, now let's try to derive the derivatives for a fully connected layer. So again, we have a computational graph of the following type. Let's just add also a bias term. So our z is wx plus b. So linear transformation, x is a vector, w is some matrix, b again is a vector, and z is our transformation. Then we calculate a. A is component-wise application of our activation function, for example, sigmoid, to this vector z, and then come L. And we calculate, okay, given the gradient of L with respect to A. Now this is just a vector, because L is a scalar, A is a vector, so this is the vector. We would like to find gradient of L with respect to Z, with respect to W, with respect to B, and with respect to X. Okay, let's do this. So how can we calculate? Well, let's start with the first thing, that given the gradient with respect to A, we would like to calculate the gradient with respect to Z. We just use this thing, the differential of our function depending on different variables. So our differential does not depend on a particular parameterization of our function. We may say that it depends on y in this case, or we may say that it depends on x in this case. Our differential doesn't change. So let's write down our differential of L in two ways. First, as a function of A. As a function of A, this differential from our table of canonical form, it is just the inner product of the gradient with respect to this parameter time this increment. So it would be the gradient of L with respect to A in a product with dA. This is from one point. Then what is dA? A, we know that this is g of z. Then we calculate the differential of A. Here z is vector, A is vector, so this is a vector valued vector function. And again, using this table, this is the case here. So this is the product of Jacobian time increment. So we need to calculate the Jacobian dg times dz times dz. And here, because our application of g of z is a component-wise, this matrix would be diagonal, because all non-diagonal elements, the derivative of ai times zj is just 0. And what we do next, we put the expression for our differential into our expression. So here, just put it here. And finally, again, we have the expression for our differentials in terms of dz. If we want to extract the required gradient of L with respect to z, we need to transform this expression into canonical form. In our case, L is a scalar, z is a vector, so canonical form looks like this. So we need to transform it to in a product of some vector times dx. So dz is stated here. This is a vector, this is a matrix, this is vector. So we may write down this like dz transposed times dz. And what is stated here is our actual gradient of L with respect to z. In a similar way, calculate the residual gradients. So now, suppose we know the gradient of L with respect to z, and we would like to calculate these three terms. So our differential of L can be expressed in two ways. From the one side, as a function of z, this is just this inner product. Then we know that our z expression is here, is a linear transformation. Then its differential is what? Just apply standard rule for differentials and put this expression back here. And finally, in order to extract our gradients with respect to individual parameters, we need again to transform this differential into canonical form. What would be the canonical form of the differential of our function L depending on three variables, x, w, and b? It would be the expression of the following form: the gradient of L with respect to w times increment w plus b db plus L with respect to x dx. This is the canonical form. So the only thing we need is to express the terms that comes as an argument at dv, an argument at db, and an argument at dx from this expression. Let's do this. So here we have a vector times matrix times vector. Vector transpose and matrix times vector. So this product is actually a real number. If we speak about real number coincides with the trace of this number as a matrix of 1 by 1. So this is the same as to say this product is equal to trace of a number. Then goes in a similar way, like here. Get the expression, and we already know two terms. So this would be the gradient of L with respect to B. This would be the gradient of L with respect to X. And finally, we need to transform this to a canonical form as a trace of some matrix times dw. And this can be easily done since, again, we can shift under the trace the product of a matrix. And finally, this is equal to trace x gradient of L with respect to z times dw plus the last part. And what is stated here, transposed, is actually our desired gradient. So the gradient of L with respect to W, some matrix, is a transposition of this. So this can be written like this. So here state the vector, the column vector, x transpose is a row vector. So this product is actually a matrix. The required the gradient of L with respect to W. And the last two things come from these two expressions. Any questions on this derivation?
No.
Okay, everything is clear.
How did we go from the trace to the gradient in the last case?
Again, we always use this table of a connection between differential and derivative. So here we have calculated a differential. This is the expression for differential. And if we want to find out the derivative, we need to use something from this table. For the case of W, W is a matrix, L is a real valued function. So we have this situation. Our standard canonical form is a trace of our gradient transpose time increment. So we need, in order to extract the gradient, we need to transform this expression into the form of trace of something transposed times dw. And this something would be exactly our derivative. And we done this by circular shift of x. We move x here, so it will be trace of something transposed times dw. So our derivative is this expression transposed. So the gradient, so this gradient times x transpose.
Thank you.
Okay, now the question to you. Suppose that in this multi-layer perceptron, you are working not with real numbers, but with complex numbers, which is, well, quite a general case. If you do some signal processing, in signal processing, it's a common situation that your axis, for example, your parameters WB are complex numbers. So let's say that X is some vector of complex numbers, W is some matrix of complex numbers, and by N, B is again some vector of complex numbers. And so this Z would be complex number, and here states some transformations that go from complex number to a real valued loss function. And you need to do the same thing. You need to do a backward propagation for calculating the gradient in your narrow network. And the interesting story is that if we speak about PyTorch, the library that we are going to use in our course, in PyTorch, you have an instrument for automatic differentiation. So you, in practice, actually don't need to derive explicitly these expressions for calculating the derivative in the backpropagation mode. Everything is done for you by the library. However, PyTorch till now does not support the backpropagation in terms of complex numbers. So it it supports the complex number itself. So if you put some complex numbers and do forward propagation, you are able to calculate this. But the computing the derivative in the backward mode does not support it. So what would you do in this particular situation? So again, our z wx plus b. So z is a vector from Cm, and then you have some loss, some real valued loss function here, and you need to calculate the gradient. Knowing the gradient of L with respect to z, calculated the gradient of L with respect to w, b, and x. What to do?
Well, we could use some expressions with imaginary and real parts of all whole matrix and vectors. So we write x is equal, for example, z plus I y, something like this, and we can differentiate this on imaginary and real part.
So express x as a sum of real and imaginary parts. And in a similar way, we do with w and b. Then we know from our backpropagation the derivative of L with respect to real part of z and derivative of L with respect to imaginary part. Then put this expression inside linear transformation. So z now opening the brackets gives us minus and this would be the imaginary part of z. This would be the real part of z. So now we have two variables, real variables that are constructed using real arguments, w, b, and x by these formulas. Then you have these two derivatives, and using the expression, you may backpropagate the gradients either using PyTorch. So when you implement just the forward pass for this calculation and automatic backward pass, or by directly deriving the expression for derivatives using these simple expressions, and in this way get the answer for complex numbers. Okay, and hopefully almost have no time. I think that we'll leave it for the next time. So to the end, we now know how to calculate the derivative of almost any complex computation for neural networks, like using some computational graphs, and it could be of arbitrary size, of arbitrary complexity. And in order to calculate the derivative, we just need to go in this computational graph from right to left. Again, you implicitly introduce this computational graph when you implement your neural network in your code by a set of forward propagation operations, calculate the derivative in a backward mode, and the only thing you need if you construct some non-trivial computational graph is to introduce the derivative calculation for each edge of this graph, and you may easily do this if you use a matrix calculus and matrix differentials, even for complex expressions. So for your homework after this lecture, you would have, well, a set of assignments of this type. So you need to, given some function or given some particular computational graph, to derive by pen and paper explicitly the derivatives and expressions in terms of matrices and vectors, etc. Okay, that's all. For now, any questions?
Okay, I have a question about complex numbers. What
The last example.
Yes, I didn't understand the key idea of this example. So you said that in PyTorch it's impossible to use complex numbers for autograd, no, for automatic gradients, and so what? How did we solve it? I didn't understand.
We replace the forward computation in terms of complex numbers to forward computations in terms of real numbers. And given this, doing everything in real numbers, you already may use autograd from PyTorch.
Okay, I got it. Yeah, thank you.
So will we need complex computations in the practice, complex numbers?
Well, the standard application is in signal processing. In signal processing, for example, Wi-Fi communication, in cellular networks, it is the standard situation when you work with complex numbers because it corresponds to a modulation process in physics, and you represent all the values, the signals in complex variables. That is why you need to, if you want to apply neural networks or any other computations, some complex computational graphs using complex numbers, you need always to think how would you transform it to something real in order to use autograd. Because, well, this is the issue in PyTorch that already several years, so many people always ask them, please add support of complex autograd. It is very required. We always use it, but the issue still is not resolved now.
But why don't they implement it? What difficulties are there?
Just working on other issues. That is, well, this is the common situation when you try to make a mathematical library, general purpose mathematical library. You need to support, well, a huge number of different mathematical operations. For example, if we speak about NumPy, at time when it was started, again, it was a huge problem, NumPy and SciPy. It was a huge problem that they started the project and many people required, please implement, I don't know, Halevsky decomposition in NumPy, eigenvalue decomposition, I don't know, optimization, numerical integration, and other thing. And people just say, and the developer just say, okay, we're working on this, but currently issue is not resolved, and it required, well, many years, I guess approximately 10 years in order for NumPy and SciPy to cover well, most of the popular mathematical operations. And the same situation is with PyTorch. PyTorch, the first version was introduced, I don't know, 2 or 3 years ago. So just the time is not enough, 3 years, to cover all the required mathematical operations.
Okay.
Okay, if no more questions, so thank you. And
one organizational question: is this time will we have elections at that time at other weeks?
Yes, this is our constant time. For now, on Fridays, starting from 10:30 to lesson, either lecture plus seminar or to lectures every Friday. Yes.
Okay.
Okay, so thank you. We'll see you in a week.
Thank you. Goodbye.
Thank you.